Most metals and conductors follow Ohm's law. That is, there is a direct relationship between voltage and current. Because resistance equals voltage over current, the resistance is constant in a given circuit. This law generally holds for both forward-biased and reverse-biased currents. This means that when there is a current or voltage going in the opposite direction, the material will still follow Ohm's law and the resistance will be constant. However, there are materials that do not follow Ohm's law, and these materials are called semiconductors. Semiconductors act in different ways when exposed to different currents and temperatures, and thus do not follow the standard graphs that Ohm's law encapsulates. One of the most common examples of a semiconductor is a diode. In a diode, in contrast with ohmic conductors, the current can only flow in one direction, forward. Ideally, no current can flow reverse-biased. However, this phenomenon in actuality often behaves differently because at high enough voltages, it is almost impossible to fully prevent current from flowing in the system. As you can see in this picture that I took that shows the resistance of the reverse bias, the resistance is a relatively high value negatively, and because resistance and current are inversely related, and the potential difference at this point is also negative, a high resistance equals a very low current. However, the current is not zero as would be ideally shown. In contrast with the reverse current, the forward current's resistance is low enough to not be detected by the same setting as the reverse. This shows that the forward and reverse bias current do not have the same relationship, and thus Ohm's law does not hold for this battery. A thermistor is a second type of semiconductor. Either the current can increase or decrease when exposed to higher temperatures. NTC thermistors are resistors with a negative temperature coefficient, which means that the resistance decreases with increasing temperature. PTC thermistors, the opposite, increase resistance with increasing temperature. I tested using a simple NTC thermistor in which I held a flame up to the thermistor and recorded the resistance at these given temperatures. A rapid initial resistance drop was followed by a plateau as shown by the graph. Lastly, I tested the forward current of a circuit in series at varying voltages. While I expected an exponential graph, I was surprised to find that the relationship I saw between current and potential difference was linear. Initially, I hypothesized that the forward current as a function of voltage would be exponential, in that a small increase in voltage would cause a great increase in current as shown below. However, as shown by my linear results, the current in the positive direction, after a certain point called VF, the current is linearly increasing, but at a low voltage to current ratio, or low resistance. Thus, through my data, the graph above was formed of the relationship between current and voltage ideally in a diode. It can be assumed that ideally there will be no reverse current because of the extremely high resistance that was seen in the multimeter that disallows for any significant current to go through at a reverse biased system. Alright, you guys have been watching my capstone for AP Physics 2. Thanks for watching, guys.